This is Dr. Shirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about binary trees, their representation using linked list. Let's start with what nonlinear data structures are. First of all, what is a data structure? Data structure is nothing but a fashion or a way in which data can be stored. Data can be stored in contiguous memory locations or discontinuous, and one data can be related to only one another database or n number of other databases. So in different ways we can classify these data structures. Data structure, if you split this word itself, data and structure, to store data in different forms. As I said, if you take a list where data is stored in contiguous memory locations. So if I'm storing an integer values in it, which take 4 bytes. So if the first location is 20, second one will be 24, 28, and so on, right? So adding 4 bytes it is going to use. For example, if I cannot find such a huge space, then I can use linked list to store the data, right? For example, the first node is at location 20, the other may be at location 54, and the third is at 39. The addresses of the next node are stored in the previous nodes, right? Current node is going to hold its data as well as the address of the next node. In these two ways, we can store the data. And structures. Structures, you can have linear and non-linear. Linear, we have the prominently known linear structures are stacks and queues. Stacks and queues, right? So stacks follow last in, first out, because you are going to put a constraint at the bottom saying that either push or pop the element only from one end. Coming to queues, it follows first in, first out. It works from both the ends, but both the ends are their work and responsibility is defined. That means the rear end is used to insert the data, whereas the front end is used to remove the data. These two are linear data structures. Coming to non-linear data structures, trees and graphs are the prominently known non-linear data structures. So, how a tree looks like? It is a top-down structure where root node will be there, which will not have any parent. That's what it is known as a node without any parent is nothing but a root, right? It can have any number of children, right? So have a look at this picture. This is how it can have. It is just a sample tree structure, non-linear. Here you can see that root is related. Say if I name root as 0, it is having 3 children, 1, 2, 3. Whereas 1 is having only one child, 4. 2 is having 3 children, 5, 6, 7. Again, 3 is having only one child, which is 8. 5 is having only one child, 9. Whereas 8 is also having only one child, which is 10. Right? So there is no restriction that one element is related to only one other element. It's not that. It can have any number of children and it can be related to any number. That is 1 to n cardinality. If you talk in terms of cardinality, it will be 1 to n. Right? So this is tree. Coming to graph. You can have directed graphs, undirected graphs. You can have weighted graphs, unweighted graphs. Right now I am showing you a small picture of a graph, right? Here node 1, 2, 3, 4, 5. 5 nodes are there. Here you can see that even it can extend to n, where n is the number of nodes in the graph. So 1 is related to 2 as well as 3. 2 is related to 1, 3, 4 and 5, right? So even it is not 1 to n, the cardinality changes. So, but on the other side, that is the right side of cardinality, you can see a numerical value which is more than 1 or more than 1. When such a feasibility is given, then it is definitely a non-linear data structure. Okay, so the basic difference between linear and non-linear. Organizing the data itself is the major difference between linear and non-linear data structures, right? So the relations which can be expressed using arrays as well as linked list also. Okay, so when we store linear structures using array, it will be beneficial. But coming to non-linear, if you store the data using arrays, it will be highly costly in nature. Costly in the sense, most of the data will be sparse in nature. So to overcome that, we use linked lists to store the data of any non-linear data structure. For example, let me give you a small example of the same. For example, a tree is something like this with the root as 0, 1, 2, 3, 4 and 5 in the level order I have given. Then using linked list, we can store the data. So 0 on the left hand side, it will hold the address of 1, right? 1 is going to hold the address of 3, and on the left and on the right address of 4. The address part of 3 left and 4 left right are null because they are the leaf nodes and they do not have any children. Coming to the right child of 0 is 2, which is not having any left child, but it has a right child which is 5. Even 5 is not having any left and right children because it is a leaf node. This is how, using a double linked list, we can store the content of any tree, right? But only binary trees, guys, because I'm specifically saying that left child, right child, and this terminology we are going to use only in case of binary trees and an extension of that, binary search trees, any tree you can use where every node can have at max 2 children. Whenever a constraint of such kind is being posed, we can have only 2 children. So left and right terminology you can use, right? So using double linked list, we can store the data of any binary tree, right? So what is a tree? Let's start from the basics. So it is a finite non-empty set of elements. Have a look at this one. So the root is animals. So reptiles and mammals are the 2 categories of animals. Coming to reptiles, you can have snakes, lizards and birds, and mammals you can have equine, bovine and canine. Okay, so many the data structure, if you draw, it will go to a lengthy way, right? So the abstract model is a hierarchical structure, and every node shares, the internal nodes share a parent-child relation. If you see between reptile and snake, snake acts as a child, whereas reptile acts as the parent of snake. Applications where you can see is any organization chart. For example, in our institute, HOI acts as the root node. He is the head of the institute, followed by the heads, HODs of various departments, say CSE, HOD of EEE, HOD of EC, right? Under the HOD of CSE, they have professors, professors. Right? Similarly for triple E as well as EC also, under each professor we have associate professors, under associate we have assistant. This structure goes on. See, organization, basic organization of our organization I have given. Okay, coming to file systems, you might have seen in file system, means in your C drive you might be having n number of folders, right? N number of folders saying storing the content like movies. Movies. Within the C, you might also have songs, and within songs, you might have different languages. You can have Hindi songs, or within songs, you can have English songs, you can have Telugu songs, right? Within Hindi, you can have the names of the movies or the albums in which you can have album 1, album 2, and so on, right? So everything in each chart, hierarchical structure if you have, it will look like a tree with the root node on its head. And every programming environment also, OS acts as the root, operating system acts as the root, right? So this is the structure of a tree. Okay, the basic terminologies which we use in terms of trees. Have a look at this one. I'll explain you these terminologies using the tree structure which I have drawn. A acts as the root. Okay, and the first slide itself, I'm using the terminology root. Root is nothing but a node which do not have any parent. Okay, coming to B, C, and D. They are children of A, as well as they are also known as siblings. In general English also we call brothers and sisters from same parents, right? We call them as siblings, right? If someone asks you who's your sibling, you're going to name the one who's your sister or brother who live with you, right? Siblings. Coming to the terminology internal node. A node which have either one or more than one child is nothing but an internal node. That is at least one child. The nodes A, B, C, and F. Have a look at them. These are the 4 nodes which have children, right? They are known as internal nodes. External nodes are a contrary to that. The nodes which do not have children are external children, also known as leaf nodes. They are denoted specifically in green color. Have a look. E, I, J, K, G, H, D, right? These are all the external nodes or leaf nodes. Okay. Coming to the terminology, ancestors. Parent, grandparent, grandparent, all that list will be ancestors. For example, who are all the ancestors of, say, J? J are, the parent of J is F, grandparent is B, grandparent is A. So, ancestors of J are F, B, and A. Just go to the root, that's it. Okay, for example, grandparents of G. So, ancestors of G will be C and A, right? So, these are ancestors. Coming to descendants, a contrary to that, child, grandchild, grandchild. For example, descendant of B. B, first of all, it is having children EF. F is further having I, J, K. So, these all people are E, F, I, J, K are descendants of B. Say, for example, A. Who are all the descendants of A? All the remaining nodes come into the picture. All the nodes are descendants of the root node. Okay. Then, what is the depth of a node? It is the length of the path from the root to the tree to M, right? When I'm talking about what is the depth of F, from the root 1 to depth is 2, right? Two edges it is sharing to reach the root. What is the depth of K? Parent, grandparent, and grand-grandparent. Three edges it is sharing. So depth of K is 3. Got it? So these are the basic terminologies which will be used when we learn trees, which will be frequently used. Roots, internal, external nodes are the most prominently used one. Okay guys, please remember that. Tree terminologies. Next, height of a node. It is the number of edges from the node to the deepest leaf is the height. What is the height of B? To the deepest leaf. Deepest is I, J, K. All three are at the same level. So the height is 2. Coming to the height of the root node. Say, what is the height of the root node A? So what is the leaf which is in the deepest leaf, that is at the last level, you can say. I, J are at the last. So 1, 2, 3. 3 edges, right? So height of A is 3. Okay. Then degree of a node. The number of children it have is nothing but the degree of a particular node. A is having 3 children, so its degree is 3. Leaf nodes. Guys, this is a very important point. The degree of a leaf node is always 0 because degree tells you about the number of children it have, but leaf nodes do not have any children. So, its degree will be always 0. Coming to the degree of B, it is 2. F, it is 3. Samples I'm giving. Okay, degree of the tree is the maximum children of its node. That is the total number of nodes that originate from it. That is 3. Degree of the tree is 3. Subtree. Tree consisting of a node and its descendant. This is nothing but a subtree. Have a look at this one. C. C is acting as a root of this subtree, which I have specified, right? And its children are G and H. We can also specify a subtree like this, where the root is B and the remaining are its descendants. Okay? I hope you understood the basic terminology of trees. Right. So, basic properties of trees, the number of nodes, the height, what is the root node, the number of leaf nodes, interior nodes, the ancestors, descendants, siblings, the right subtree, left subtree, or degree of the tree, all are the basic properties of any tree. Coming to a specific tree, which is a part and parcel of our subject, is a binary tree. Binary tree is a tree in which we put a constraint that it can max have only 2 children. Have a look at this picture. 2 is having only 2 children, 7 and 5. 6 is having only 2 children. 9 is having only 1 child. 5 is having only 1 child. If you look at the degrees of each node, it can have a max degree of 2. Any node can have a max degree of only 2, right? Such a tree is known as binary tree. So, types of binary trees, the variants. We have basically 5 variants of binary trees. Guys, these are very important. Few formulas will be there. Please make a note of them. Okay. What is a full binary tree first of all? Full binary tree is also known as strictly binary tree. Okay. It is a tree in which every node can have either 2 or 0 children. Have a look at the picture here. 4 and 8 are the nodes who have 2 children each. Whereas 2, 6 and 10 are the nodes which have 0 children. Okay, that means that every node can have either 2 or 0 children, then we call it as full or strictly binary tree. Then the number of leaf nodes in a full binary tree is 1 plus the number of internal nodes. So that is here the number of leaf nodes, L is, and the capital I is the number of internal nodes. Then have a look at this one. 8, 4 are the 2 internal nodes. So I is equal to 2. L is equal to 2 plus 1 as per formula, which is 3. So 2, 6 and 10 are the 3 leaf nodes. Yes, please remember this formula. Complete binary tree. A complete binary tree says that all the leaf nodes will be at same level. Okay, so have a look at this one. Is a binary tree will be called as a complete binary tree if all levels are completely filled except possibly the last level. And the last level, all the keys are left as possible. For example, I have a tree, a similar one I'm going to show you guys. 10, 2, 6, 5. Have a look at the tree which I have given over here. Here, level 0, root is present. Level 1 must be filled with 2 values. That is, one is left value and the other is right value. It is filled. Coming to level 2. The first node, 4 is having 2 children. 10 is having a single child. And even though level 2 is not completely filled, but all the elements are filled from left to right. Have a look at this one. Only the right child of 10 is missing. But have a look at the diagram or the binary tree which I have drawn. 0th level is full. First level is full. Coming to the second level, before filling the right child of 4, they directly went to fill the left and right children of 10. Such a tree is not a complete binary tree. It is not a complete binary tree. So here is the basic formulas which you need to learn. The number of nodes in a complete binary tree are 2d plus 1, 2 per d plus 1 minus 1, where d is the depth. Where d is the depth of the tree. And the number of leaf nodes is 2 to the power of d. Again, where d is the depth of the tree. Here the depth of the tree is 2, right? So the number of nodes you can have is 2 power d plus 1 minus 1 1, 2 to the power of 2 plus 1 minus 1, which is 2 cube. 7 you can have. If you completely fill it, say with some value 11, how many nodes you have? 7, right? So the number of leaf nodes is 2 per d, which is 2 square 4. How many leaf nodes do you have? 4. Satisfied or not? All the 4 formulas, or both the formulas, the number of total nodes and the number of leaf nodes depends upon the depth of the tree. Okay, this is about complete binary tree. Okay, let's go with the next one. What is a perfect binary tree? Guys, all these variants are binary trees with a hairline difference. Okay, so please keep that hairline difference in your mind. So a binary tree is known as a perfect binary tree in which all internal nodes have 2 children and all leaves are at the same level. Right? So such a tree is known as perfect. It is perfect in all terms. Have a look at this one. 0th level is filled with 8. First level is filled with 2 elements. Second level is filled with 4 elements. You do not find any vacant one, right? And all the leaf nodes are at same level, which is level 2, right? This kind of tree is nothing but perfect binary tree. And coming to the perfect binary tree height, okay, has 2 power h minus 1 nodes. The number of nodes in a perfect binary tree of height h is 2 power h minus 1. Here the height is 2. So 2 square minus 1. Okay. So this is a perfect binary tree. Coming to balanced binary trees. A balanced binary tree is a tree in which the height h is such that height of any nodes right subtree and left subtree differ by 1 or 0, but not more than 1. Okay. For example, have a look at the left side figure where the height of the left subtree of 1 is 2, right is 3. 2 minus 3 is minus 1, right? So what did I tell you? The difference between the heights of the left and right subtree must be either 1 or 0, plus or minus 1. It depends upon the height of left and right? So it will be either plus or minus 1. The balance factor, generally we call it as the difference between the heights of left and right subtree is nothing but balance factor. And if the balance factor is minus 1, 0 or 1, then we call it as a height balanced tree. And this balance factor rule, each and every node, including the leaf node, must abide to that. Obviously, for the leaf nodes, balance factor is 0 because they does not have any left or right subtrees. So, okay, coming to the tree which is on my right side. Left side height is 1, right hand side height is 3, which is minus 2, which is not abiding the rule of balance factor. So it is not a height balanced tree. Okay. Balance is based upon balance factor, which can be either minus 1, 0 or plus 1. Okay. That is balance factor is height of left tree minus height of right. But all the nodes. Okay. Please make a note of this one. Next. Left skewed and right skewed trees. If you insert an element only on the left hand side and the length, and you can see that all the nodes in a binary tree are having only left elements and 0 right elements, then it is known as left skewed tree. If you insert all the elements only in the right side direction, that is, all the nodes in the tree have only right child but no left child, then it is known as right skewed tree. Okay. So how we represent these binary trees? So we can represent them sequentially using arrays, or we can even use linked list to represent. Okay. So let's say a sequential way how we can represent a binary tree. Okay, guys. So have a look at this tree. Okay, so have to give numbering index. See, if we are storing data in terms of array, we need to follow the index values. Am I right? So have to give index values to the elements in a tree. Simple. Start with the root, because every tree, if there is a tree existing, then it will have at least one node which will be the root. Root will always have the index value 0. Its left child will have 1, right child will have 2. The left child of 4 here in terms of 4 will have index value 3, and its right will have 4. Even if it is not there, we have to leave space. Coming to the left child of 2, which is named as 5 and right is named as 6. Have a look at this picture. Even though the element 4 is not having any right child, 2 is not having any left child, we have to give empty space over there. Have a look at this one. In the array also, I have left these spaces as blank. Okay, to represent a binary tree of depth D using arrays, we need a maximum size of 2 power d plus 1 minus 1. That means you need to think of a perfect binary tree. The number of elements in a perfect binary tree is 2 power h plus 1 minus 1, right? So similarly, if you want to store a binary tree of certain depth, you need to have 2 per d plus 1 minus 1 spaces. Even if it's a few nodes are have missing few left and right subtrees, we have to allocate some empty spaces to them, because in future they may get filled. For example, a root node is something like this. It is having a left child, a right child. Left is having a left, a right, right. So what will be the index values? 0, 1, 2, 3, 4, 5, 6. 5 is vacant, my dears. 7, 8. Okay, 9. 8 and 9 are vacant. 10. And coming to the, guys, even though 5 node is not there, what if in the future, if it gets a left and right? So 11 and 12, the left and right for 5 must be left vacant. 13 and 14, even the 14 right of 6 is not there, you have to leave a space. Left of 7 is not there. 15 and 16. Think, guys, what is the depth of this tree? 1, 2, 3, 4. D is 4. So even though nodes 8, 9, 10, 11, 12, 13, 14 are not having any left and right chairs, you have to give some space to them, because the number of locations will be d plus 1 minus 1. That is 2 power 5 minus 1. You are having actually 3, 6, 9, 10 nodes, but you will be using more. That is the size of the array which is used to store this tree will be high, because the depth is 4, even though, and the last level you have only one element. You have to allocate space for the empty one also, because in the future, if it extends itself to a perfect binary tree, those cells must be there to be filled in the future, right? So that is the basic drawback that you're going to encounter when you implement the representation of a tree using sequential manner, that is arrays, right? So the advantage is direct access. Just by level order indexing, you can retrieve any value, as indexes are the basic advantages of arrays. With index value, you can navigate from one node to the another node in your wish, right? Basic drawback is you should know the height of the tree beforehand to implement this one, right? What is the height, maximum height your tree can extend? What if it extends? If it extends, the size of the array which you use is going to stretch exponentially, which is highly costly in nature, right? That is the basic disadvantage of implementing binary tree using arrays, that is its sequential order. Insertion and deletion of a node is also very difficult, guys. Please remember, you need to search for that particular index value. If it's left and right children are not there, you have to search for it, and it is a very tedious task. And array which you are going to take, if the binary node is sparse in nature, the array will also be sparse in nature and huge wastage of memory will be there. Okay, to overcome that, we can go for linked representation. We can use linked list. As I have shown previously, this tree can be used, that is double linked list can be used to represent a binary tree, right? And this is the structure of a node. Every node will have three parts. The center part will be a data part which holds the data. Left part will hold the address of the left child, and right part will hold the address of the right child. Okay, for example, say 8 is at location 2000. Its left child is at 4000 and right child is at 8000. Then this 4000 is the location of left and 8000 is the location of the right child. Whereas the node 6 is at location 4000, it will be saying that my left child is at 1000 and right child is 1500. That means the node 2 is at location 1000, whereas its right child is at 1500. Coming to 10, node 10, which is located at location 8000, it is saying that its left child is at 9000, right child is at 2500, say. So 11 is at 2500 and 9 is at location 9000. And as you can see, 2, 4, 9 and 11 do not have children. They are the leaf nodes. As they are the leaf nodes, as they are the basic leaf nodes, its left address part and right address part are filled with none, saying that they do not have children. Okay, like this you can use a list, that is a linked list basically, to represent a binary tree. Okay, so the basic advantage is you need not know the height. You can extend. If I insert a node as a new node, introduce a new node as the child of any leaf node, just create a node and put addresses, fill the address spaces, that is enough, right? So height, knowing the height, which used to be a prerequisite when used to represent a binary tree sequentially, is no longer a prerequisite over here. Okay, memory wastage will not be there when compared to your array representation. Insertion and deletion are very easy. Just know them, delete them. To understand this, how to insert and delete an element in a double linked list, please follow my video which is posted on our college YouTube channel. On our college YouTube channel, the insertion and deletion operations in a double linked list, you'll understand it. Quite easy and very simple, very less complex. Okay, coming to the disadvantages. As it is a tree structure, always accessing will be start from the root. Whatever operation you take, guys, whether you want to go for search, insert, delete, the three prominent operations that we generally perform, you have to always start from the root, because it is the only address that we have in our hands, the root node's address, right? So direct access is difficult, and the basic disadvantage which a linked list suffers, which is storing of the address. Every database will have an address slot, right? The number of bytes which are used to store the address are been wasted. And it is a double linked list, that means two addresses you are going to store in any node, right? So the amount of, in general, if I say, the amount of bytes you use to store the data will be very less when compared to the amount of memory which you are going to use to store the addresses, right? That is the basic disadvantage. Okay, that's the most prominent one. These are the disadvantages of your linked list, right? When you represent the data using linked list. So by this, we can say that, guys, non-linear and linear data structures are the two basic divisions of your data structure, where non-linear data structures are used for storing the data, which is where the relation between the data items is not one to one, and a tree structure is most prominent one in any organization structure on a data storing structures. If you see in DBMS or any language you want, you will definitely find the structure of a tree. In this lecture, you have learned what a tree is basically, what are the basic terminologies which we use for trees, followed by binary tree, what a binary tree, what are the variants of a binary tree, how to represent a binary tree using graphs, using your arrays as well as linked list, their pros and cons, right? I hope this video have given you enough knowledge on what basically tree is and binary trees. In my coming videos, guys, you can search for BSTs, binary search trees. So the basic difference between binary tree and binary search tree is binary tree do not impose any restriction on the data which we store. So on the left of 2, you can have a value 4 which is greater than 2, and on the right hand side you can have a value 1 which is less than the root, whereas left of 1 is 10, right is 5, 2 is 3, this is again 15, something like that. If you write an in order, post order, pre order, any traversal of your interest, if you write, you'll not find that the data is in ordered state. So BSTs overcome that. In BSTs, binary search trees, they impose a rule saying that the left node of any tree, the left node of any tree must have a value which is less than or equal to its parent, whereas the right child must have a value which is greater than its children. Then what is the advantage of this one? The basic advantage is when you write the in order of this one by BST, you will get a sorted list, ascending ordered sorted list, which is highly useful when you perform insertion and deletion operations. To understand this with examples and pseudocode of the same, please check my next video on binary search trees. Okay, guys? Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.